Welcome to SpecClaw, a tool tutorial for all BISTEC developers. This is a 4-hour session focused on spec-driven workflow with Claude Code. You will learn how to write structured change proposals, generate implementation specs, execute task waves, produce automated pull request bodies, and build a durable audit trail for every feature you ship. The session is cross-track, meaning it applies regardless of whether you work as an engineer, tech lead, architect, or QA lead. The only prerequisite is familiarity with Claude Code basics and how marketplace plugins expose/commands. The SpecClaw plugin lives at github.com/chanfolke SpecClaw. By the end of this session, you will have run the full workflow end-to-end on a real BISTEC project. When you use an AI assistant to write code without a spec, several problems appear predictably. The model expands the change beyond your original intent, scope drift. There is no audit trail, so it becomes impossible to explain why a specific file changed. Without acceptance criteria, there is no pass or fail signal. The output is untestable. Reviewers question decisions the AI made silently, creating friction, and rerunning the same prompt produces a different result, making the build irreproducible. SpecClaw addresses every one of these. A proposal defines exactly what changes and what does not, bounding scope before any code runs. Every decision is traceable to a written spec. Acceptance criteria are tested before the pull request opens. The PR body is generated from the spec automatically. And task waves produce consistent, repeatable builds. The core idea is simple. Write the spec before the code, not after. SpecClaw enforces that order through its /command workflow. The SpecClaw workflow has 7 steps in a fixed sequence. You start with /SpecClaw init to configure the project, setting the model per phase, and the Git strategy. Then /SpecClaw propose to author a change proposal with a problem statement and scope. /SpecClaw plan generates the full spec, acceptance criteria, technical design, file-level mappings, and task waves. /SpecClaw build executes those task waves in dependency order. /SpecClaw verify checks the output against every acceptance criterion. /SpecClaw per-assembles the pull request body from the existing artifacts and opens the PR. Finally, /SpecClaw archive seals the change bundle into long-term storage inside .speclaw/changes. 4 properties run through the entire workflow: spec before code, traceable decisions, automated PR body, and a durable archive. Each step produces a file that the next step reads. There is no step that requires information outside the spec. You run /SpecClaw init once per repository. It creates the .speclaw directory and prompts you for 3 configuration choices that live in .speclaw/config.yaml. The first choice is model per phase. You select which model handles planning, which handles coding, and which handles reviewing. The default configuration uses Claude Opus for planning, GPT 5.1 Codex for coding, and Claude Sonnet for review. This is the primary cost control lever in SpecClaw. You can tune each phase independently. The second choice is Git strategy. The default is branch. SpecClaw creates a feature branch and works there. Worktree gives true isolation from your working tree. Direct commits to the current branch without branching. The third choice is integration. GitHub, Azure DevOps, or Jira. This controls how /SpecClaw per links pull requests back to tickets. One important note: /SpecClaw init must run before /SpecClaw propose. The .speclaw directory must exist first. The quality of your proposal determines the quality of everything downstream. A strong proposal describes one shippable behavior, one new endpoint, one UI component, one service method, with a specific, testable problem statement tied to a real project need. Consider a concrete example of a strong proposal. The problem: the /user's endpoint returns 200 even when the user does not exist. The scope: 3 specific files, the route handler, the error middleware, and the test file. Out of scope, auth changes, and pagination. That proposal gives the planner model everything it needs to generate precise acceptance criteria and file mappings. A weak proposal says things like, the API has some bugs and is hard to use, with a scope of various route files. That produces an unmanageable spec and unreliable file mappings. 2 anti-patterns to avoid: proposals that span multiple features, and proposals with vague scope. Narrow and testable is the goal every time. Every change you run through SpecClaw produces a structured set of files in a named subdirectory under .speclaw/changes. For a change called addUsers404, you get a proposal.end, a spec.end, a design.end, a tasks.end, an errors.end, a learnings.end, and a verify report.end. Proposal.nd contains the problem statement and scope, written before any code exists. Spec.end contains the acceptance criteria, technical design, file-level mappings, and task wave list, generated by /SpecClaw plan. Errors.md records build failures per task. Learnings.md captures spec gaps and patterns discovered during the build. Verify report.end contains expected versus actual outcomes for every acceptance criterion with a pass or fail result, generated by /SpecClaw verify. The audit value of this structure is significant. Any team member can open .speclaw/changes and answer the question, why did this file change? Without asking the author. 6 months after a merge, the full decision trail is still readable. After writing your proposal, /SpecClaw plan generates the full spec document. The most important thing to do before running /SpecClaw build is to read the generated spec.end and confirm that the wave ordering looks correct. A well-formed spec has 4 sections. Acceptance criteria are numbered, independently verifiable conditions, AC1, AC2, AC3, that /SpecClaw verify will test one by one. The technical design section records architectural decisions and data flow. File mapping state, which source files each task reads and writes, enabling precise change attribution. The task waves section lists groups of tasks in dependency order. If after reading the spec you find that the wave ordering is wrong, or that the acceptance criteria are ambiguous, the right action is to refine your proposal and rerun /SpecClaw plan before building anything. Catching a spec problem at this stage costs seconds. Catching it after a build has run costs significantly more. Task waves are the mechanism SpecClaw uses to control parallelism and dependency ordering in a build. A task wave is a group of tasks that share no interdependencies. All tasks in the same wave can run concurrently. Wave ordering means wave 2 only begins after every task in wave 1 completes, preventing any task from consuming inputs that do not yet exist. Consider the addUsers404 example. Wave 1 contains 3 tasks. Add the 404 branch to the root handler, update the error middleware, and update the type definitions. These 3 tasks are independent of each other, so they run in parallel. Wave 2 contains the test files, a new not found test, and an updated integration test. Both test files depend on the Wave 1 root and middleware changes, so they wait until Wave 1 completes. Every task in the spec declares its inputs explicitly, making the build graph auditable. You can read spec.end and trace exactly which files each task reads and writes. SpecClaw assigns a different Claude model to each phase of the workflow. The planner model, used during /SpecClaw plan, is optimized for reasoning depth. Claude Opus is the typical choice. It runs once per feature to produce the spec, acceptance criteria, and task wave structure. The cost is higher per token, but it runs once. The coder model used during /SpecClaw build is optimized for code generation throughput, GPT-FIT1 codecs by default. It executes every task in every wave. The cost is lower per token, and it runs many times across all the files in all the waves. The reviewer model, used during /SpecClaw verify, reads the build output and checks it against acceptance criteria. Claude Sonnet by default. It does not generate code, it reads and evaluates. Mixing models per phase is the primary cost control lever in SpecClaw, without sacrificing plan quality. Model selection lives in .speclaw/config.yaml and is logged in every build record, so you always know which model produced a given spec. /SpecClaw build reads the task waves from spec.end and executes them in order. Wave 1 tasks run concurrently using the coder model. When all Wave 1 tasks complete, Wave 2 begins. Failures are written to errors.end. Patterns and insights discovered during implementation are written to learnings.end. An important constraint: the challenge requires all waves to complete without manual intervention between them. If a wave fails, you read the error in errors.end, revise the relevant section of the spec, and rerun /SpecClaw build. You do not hand-edit the wave output. The discipline of not touching the output manually is what keeps the audit trail intact. If you hand-edit, the build log no longer reflects what actually happened. Most wave failures trace back to an imprecise spec section, either a task that was underspecified or a file mapping that was incomplete. The fix is upstream in the spec, not in the code. /SpecClaw verify tests every numbered acceptance criterion from the spec independently, using the reviewer model. For each criterion, it records the expected outcome, the actual outcome, and a pass or fail result. The full output is written to verify report.end. When a criterion fails, the output tells you the root cause. The correct response is to fix the code or refine the spec and rerun. Both the initial fail result and the subsequent pass result should appear in the verification report, showing the fix matters as much as showing the pass. The challenge requires at least 2 of 3 acceptance criteria to pass on the first /SpecClaw verify run. That constraint exists to push you toward investing in proposal quality before building, rather than iterating on broken output. Think about what a verification failure tells you about plan quality. A failing acceptance criterion often means the spec was underspecified or the proposal scope was broader than the planner model could resolve cleanly. The failure is diagnostic information about the planning phase, not just about the code. /SpecClaw does not author any new content. It assembles the PR body from the files that already exist, proposal.end, spec.end, and verifyreport.end. The resulting PR body contains a summary, the problem statement from the proposal, the change scope, the acceptance criteria from the spec, the verification report, a link to the .speclaw/changes bundle, and a wave summary showing how many tasks ran in each wave. The PR is then created on GitHub or Azure DevOps with the assembled body. The title follows conventional commits format, fix, feat, refactor, based on the proposal type. One constraint applies in the challenge: the PR body must match /SpecClaw output exactly. No hand edits are allowed. The evaluator will compare the PR body to the /SpecClaw output. This constraint reinforces the same discipline as not editing wave output. The automation produces the record, not you. /SpecClaw archive runs after the PR merges. It adds an archive meta.json file to the change bundle containing the PR URL, the merge date, and the branch name. That addition seals the bundle. It transitions from a work-in-progress directory to a permanent record. The value of the archive becomes apparent over time. 6 months after a feature ships, any team member can open .speclaw/changes and trace every code decision back to a written proposal and a specific acceptance criterion. The technical design, the file mappings, the errors and learnings logs, and the verify report are all preserved in a structured, readable format. This kind of structured record is also useful for compliance and retrospectives. An audit asking, "Why did this code change, and was it verified?" has a complete, machine-readable answer in the .SpecClaw directory. The challenge requires running /SpecClaw archive after the PR merges. The evaluator will verify that the change bundle is present and contains all 4 files plus the archive meta.json. The session runs for 4 hours in a structured sequence. Hour 1 is Why Spec-Driven? Starting with an introduction to the problem with unstructured AI-assisted coding, then a lecture covering the full SpecClaw workflow model, followed by a case study tracing a completed .SpecClaw/changes directory, and closing with Q&A on workflow stages. Hour 2 is Config and Proposals, a configuration deep dive covering model selection, Git strategy, and integrations, followed by a hands-on workshop where you run /SpecClaw init and /SpecClaw propose on a sample repository, then a group discussion on what makes a strong problem statement versus scope creep. Hour 3 is hands-on build. You confirm your setup, then run /SpecClaw plan and /SpecClaw build on a feature from your own BISTEC project. The hour closes with a checkpoint where the facilitator reviews 2 .SpecClaw/changes outputs with the group. Hour 4 is Verify, PR, Wrap-Up, the Verification Lab, volunteer presentations of generated PR descriptions, and the session wrap-up covering offline milestones and the challenge briefing. Before the workshop portion of the session, verify 5 things. First, Claude Code version 2.1 or later, run Claude -- version to confirm. Second, the SpecClaw plugin installed, run /plugin marketplace add /chenfolke/SpecClaw, then /plugin install SpecClaw at /chenfolke. Third, a real BISTEC project repository where you have write access. Confirm you can push a branch, not just clone. Fourth, GitHub CLI authenticated, run auth status to confirm, or an Azure DevOps personal access token configured. Fifth, Node EGS 18 or later if your target project uses JavaScript or TypeScript. 3 common setup pitfalls to watch for. Choosing a repository where you have read-only access will cause /SpecClaw build to fail when it tries to push. Forgetting to run /SpecClaw init before /SpecClaw propose will produce an error because the .SpecClaw directory does not exist. Using the worktree Git strategy without understanding the implications, the branch strategy is the safe default for this workshop. The challenge has 4 deliverables, each worth 25 points for a total of 100. You need 75 points to pass. The first deliverable is a change proposal, a specific problem statement, concrete scope listing 3 to 5 files, explicit out-of-scope items, and the /SpecClaw propose output pasted verbatim into your submission. The second deliverable is an implementation spec and build bundle, spec.md with at least 3 acceptance criteria, at least 2 task waves, errors.end showing all waves complete with any failures documented, and the feature branch pushed to the remote. The third deliverable is a verification report, the full /SpecClaw verify output showing expected versus actual for each criterion, any failing criterion documented with the fix applied, and the model configuration recorded. The fourth deliverable is a merged PR and retrospective, the PR body matching /SpecClaw per output exactly with no hand edits, the PR merged /SpecClaw archive run, and a retrospective containing genuine insight rather than a summary. Key constraints: 1 shippable behavior per proposal, no manual edits between task waves, PR body unedited, at least 2 of 3 acceptance criteria passing on the first verify run, and branch as the Git strategy unless you have facilitator approval for worktree. After the session, 5 offline milestones help you deepen your understanding of SpecClaw. The first is to run a second feature end-to-end and compare two .SpecClaw/changes bundles from the same project. Notice how the proposal scope affects spec complexity. A narrower proposal produces a leaner spec with cleaner wave boundaries. The second is to switch the planner model. Run /SpecClaw plan with Opus, and then with Sonnet on the same proposal and compare spec depth, wave count, and acceptance criteria quality. This experiment produces real data about the cost-quality trade-off for your specific type of work. The third is to try the worktree Git strategy on a branch where you want true isolation from your working tree. Observe how the file layout differs from the branch strategy. The fourth is to configure Azure DevOps or Jira integration and observe how /SpecClaw per links to a ticket automatically. The fifth is to write a one-page summary for your team lead on whether SpecClaw should become a standard tool on your project and what would need to be true for that to happen next sprint. 5 ideas to carry out of this session. Spec before code. Write the proposal and plan before any file changes. The order SpecClaw enforces, propose then plan then build, is the discipline that makes AI-assisted coding auditable and reviewable. Bounded scope wins. A narrow, testable proposal produces a better spec than a broad one. Scope 1 shippable behavior per change and your task waves will be clean. Task waves are explicit. Parallelism in your build is controlled by wave ordering. Wave n+1 inputs are wave n outputs. There are no hidden dependencies. Multi-model means cost control. Use Opus for planning depth and Sonnet for coding throughput. Set it once in config, and it is logged in every build record. PR body is automatic. /SpecClaw per assembles from the artifacts you already produced. No manual writing, and no reviewer questioning undocumented decisions. The plugin is at github.com/SpecClaw. The conventional commits format used in PR titles is at conventionalcommits.org. GitHub CLI documentation is at cli.gith.com.